Hey there, folks. Welcome to the super awesome recorded lecture for the beginning of Unit 1. So, let's get started. Okay, our learning objectives for today, we are going to review very quickly 1.1 and 4.5, which are both review objectives from previous chemistry classes. So 1.1 is the idea that we can convert between grams, moles, and particles. And 4.5 is using a balanced chemical reaction equation to determine different quantities, also known as stoichiometry. We're not going to hit stoichiometry too hard. It's just something that I want you to remember that you knew how to do at one point in time. Today, we're going to focus on how we can apply 1.1, so converting between grams and moles, to determine the formulas for different compounds based on experimental evidence. In the slide deck, there are links to the sections in our OpenStax textbook that will take you to each of those. And if you want to jump to the specific topic, you can click the topic link over on the left-hand side, and it will take you specifically to those topic slides. But let's jump in and start at the beginning. Okay, so topic 1.1, moles and molar mass. As you may remember, we can count very small objects or very large numbers of objects by using the average mass of a single item. My non-chemistry example here is jelly beans. If you have a giant container of jelly beans, but you know the mass of one jelly bean, you can determine how many jelly beans are in the giant container by looking at its total mass. Same with molar mass. The molar mass of a compound tells us the average mass of 1 mole or 1 particle of that particular chemical formula. So to calculate molar mass, we use the atomic masses. So each element has an average atomic mass, which we will look at later. It's a weighted average of all isotopes of that element. We've learned a little bit about that previously. We're going to look at that in more detail in a later lesson. When you add them all up, we get what's called the molar mass. To convert between grams and moles, you either multiply or divide by the molar mass. So remember that our molar mass has units of grams per mole. So if we are starting with grams, we are going to multiply by 1 mole over the molar mass in grams, which is also the number of grams divided by the molar mass. If we are going from, I wrote that in the wrong spot. I wasn't even paying attention to the graphic here. Let's move that down there. That makes more sense. If we're going back the other way, if we are going from moles to grams, so if we're starting with our moles, we multiply by the molar mass in grams over 1 mole, because again, molar mass is the mass in grams per 1 mole of that substance, which is also our number of moles just times the molar mass. Okay, moving on. We use molar mass because a mole is a set number of particles. Okay, so a mole is the same number of particles. It's 6.022 times 10 to the 23rd. We call that Avogadro's number. Avogadro here is underlined. Avogadro was a guy. If you follow that link, it'll take you to, I believe, his Wikipedia page if you want to learn a little bit more about him. 1 mole of a molecule will contain the same number of moles of each element equal to the number of atoms in each element of the compound. So we're going to use water here as our example. So we have a single molecule of water, so 2 hydrogens and an oxygen. In 1 mole of water, we're going to have 6.022 times 10 to the 23rd particles of water. Now, because every 1 water has 2 hydrogen and 1 oxygen, that means we have in 1 mole of water, we have 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So we can set this up almost like a ratio. So for every 1 mole of H2O, we have 2 moles of hydrogen because we've got that 2 as a subscript. And for every 1 mole of water, we get 1 mole of oxygen particles because we just have 1 oxygen atom in a formula of water. We're going to use this to determine formulas by looking at individual masses. Quick reminder, if we wanted to calculate the molar mass, we'd add up the mass of hydrogen times 2, because there's 2 hydrogens, plus the mass of oxygen, and that would get us the molar mass of water. So if we can convert between grams and moles, we can also convert between moles and particles. Not something we have to do very often, but it is something to keep in mind. It is a conversion that we can do. So going from number of molecules to moles, we're going to divide by Avogadro's number. Going from moles then to grams, we're going to multiply by the molar mass. We go from grams to moles, we're going to divide by the molar mass. And then going from moles to molecules, we're going to multiply by Avogadro's number. So they go opposite of each other. If you're going to multiply by the molar mass, you're going to divide by Avogadro's number. If you're dividing by the molar mass, you're going to multiply by Avogadro's number. That's because each of these are in relation to 1 mole. So molar mass is the mass of 1 mole of a substance, whereas Avogadro's number are the number of molecules in 1 mole of a substance. So both of these are in relation to 1 mole of stuff. Okay, so when we have balanced chemical reaction equations, we have coefficients that tell us the ratio of the compounds and how they react. So we balance reaction equations so that we have law of conservation of mass. So in this particular example, if we're reacting hydrogen with nitrogen to make ammonia, NH3, we originally have 2 hydrogens, so hydrogen, and we have 2 nitrogens, nitrogen and nitrogen, and when they bond, they form nitrogen plus 3 hydrogens. We're going to worry about the bonding later. We'll learn how to draw these, or we'll remind ourselves how to draw these. Now, law of conservation of mass tells us that we can't go from 2 nitrogens down to something that just has 1 nitrogen. So to solve that, we're going to double our amount of ammonia because we know that we're starting with 2 nitrogens, so we need to end with 2 nitrogens. Now, we're ending here with 6 hydrogens. We only start with 2. Well, we can't just randomly lose 4 hydrogens, so we really, instead of having 2 hydrogens, we really have 6 to start with. So since we have 1, 2, 3 hydrogen molecules, we put a 3 as its coefficient. We have 1 nitrogen molecule, so we have 1 as its coefficient. And we have 2 ammonia molecules, so we have a 2 as its coefficient. This tells us the ratio. So lowest possible whole numbers that these things are going to react. If you have 1 nitrogen, you have to have at least 3 hydrogen molecules, and you will always make 2 moles of ammonia. If we have 2 nitrogen molecules, we're going to need 6 hydrogen molecules, and we'll make 4 ammonia molecules. So here's a worked through example to remind you of the dimensional analysis and how this is set up. This is something that we're going to come back to later, and we will refresh and build in as we go. Again, this is a reminder that you've done this before. You know how to do this. If you want some practice with molar mass, mole conversions, or stoichiometry, each of these links will take you to the ChemQuiz website, where you can practice as many times as you would like. If you want more practice from me, let me know. But let's go apply these things. Okay, so first up, we're going to look at the composition of pure substances based on individual amounts of elements. So pure substances can be considered elements or compounds as long as it's just one, as long as a sample is just one type of thing. It can be individual atoms, it can be atoms bonded together, as long as the atoms bonded together are the same in every unit, the same in every particle. We describe these pure substances using chemical formulas. Chemical formulas are governed by the law of definite proportions, which was developed by Joseph Proust. Again, you can follow the link to read a little bit more about him. A given compound is always going to contain the exact same proportion of elements by mass. This means that if something has 2 hydrogens and 1 oxygen, it will always be water. If it's in a different ratio, for example, 2 hydrogens and 2 oxygens, that is hydrogen peroxide. It is not water. The chemical formula tells you exactly what something is. Now, there are really 2 types of chemical formulas. There's an empirical formula and there's a molecular formula. They can be the same, but they may not be the same. The molecular formula is going to tell you exactly how many atoms of each type of atom are in a compound. Okay, this is what we use our molar mass for. This is what we think of in terms of reflecting the actual compound, the actual particle. The empirical formula is the lowest whole number ratio. So, for example, H2O, hydrogen peroxide, has 2 hydrogens and 2 oxygens. That's a 2-to-2 or a 1-to-1 ratio. We can reduce that to 1 hydrogen, 1 oxygen. That's not what's actually in the compound. The compound is 2 hydrogens, 2 oxygens. So the empirical formula is HO. The molecular formula is H2O2. For water, its empirical and its molecular formula are exactly the same, okay? Because 2 hydrogens to 1 oxygen can't reduce to any lower whole numbers. So when we go to figure out what these ratios are going to be, we have 2 different types of lab analysis technique. We've got gravimetric analysis, which is where we use accurate measurements of mass, often heating until a constant mass. We're going to do this in lab next week, where we are going to dehydrate a particular compound and make mass measurements to then look back at what its original formula was. There's also a lab technique called compositional analysis. This is not something that we can necessarily do in lab. You need more you need better equipment than what we have. But what we're looking at here is a determination using percentages. So if something tells me that it's X percent hydrogen and Y percent oxygen, we can figure out what the original ratio was. When we use this analysis technique, we're going to assume that we have 100 grams of a sample. You can assume any mass of a sample, but if you assume 100 grams, your percent is your mass, because a percent of 100 is the same number. So let's make life easier for ourselves. We're going to take the mass percent, automatically assume that we have 100 grams. Therefore, the mass percent is going to tell us the mass of each element. We're going to use the molar mass to convert to moles, because that's how we look at ratios. We look at ratios in moles. Remember, grams is the mass, so how much stuff there is, whereas moles tells us the number. When we're looking at ratios, we need to look at the ratios of the numbers of particles. From there, we can determine the mole ratio and get us to our empirical formula. Another technique that we have is called combustion, where we burn the substance. This works really, really well for substances that have carbon, hydrogen, and oxygen. So what we look at when we burn these types of substances, we will always get carbon dioxide and water as a product. There we go. That's the right word. Then we can use the mass of the carbon dioxide and the mass of water to figure out the moles of carbon, moles of water, moles of oxygen to determine what the empirical formula would be. Okay, so let's look at an example here. we've got 1.258 grams of copper chloride hydrate. So that means for every copper chloride particle, we've got some amount of water attached to it. And I already found a typo in my slide. That should be H with a subscript 2O. Okay, this was heated in a crucible. Well, what happens when water gets heated? It evaporates, okay? So the water evaporates, it turns into a gas, it goes away, it leaves our sample. So then we cool it down. The final mass is 1.012 grams of copper chloride. We don't know what the particular ratios are right now. The copper chloride sample was dissolved in 50 milliliters of deionized water, and 0.2 grams of fine aluminum mesh was added to the beaker, okay? After reacting and dissolving the excess aluminum, 0.479 grams of dried copper metal is recovered. Okay, so let's look at the information that we have. We know that we are starting with 1.012 grams of copper chloride, some amount of copper, some amount of chloride. We know that at the end, 0.479 grams of that is copper. Okay, so I've got 0.479 grams of copper. If I want to know how much chlorine I have, I am going to take my copper chloride mass and then subtract my copper mass. Law of conservation of mass, oops, that's supposed to be a 9. Law of conservation of mass tells us that anything left over, anything that's not copper, had to have been chlorine, right? Because we can't have, we're assuming a pure sample here, okay? So 1.012 minus 0.479 gets us 0.533 grams of chlorine. Okay, so I've got 0.533 grams of chlorine. And then we're going to do something similar with our original compound. So if we started with 1.285 grams of this hydrate, and after we drove off all the water, we had 1.012 grams left, the difference between those two is how much water there was. So 1.285 minus 1.012, 0.285 minus 1.012 gets us 0.273 grams of water. Okay, so now we know each of our components. So we are going to convert all of these into moles, because when we're looking at chemical formulas, we're looking at mole ratios. Okay, so we're going to use our periodic table here. So 1 mole of copper is, this would be useful if I had my periodic table in front of me. Come on. Okay, there we go. 63.55 grams. My molar mass of chlorine is, looking in the wrong spot, 35.45 grams. And then my molar mass of water is 2 hydrogens plus 1 oxygen. So hydrogen is 1. What's our periodic table say? Periodic table says 1.008. So we're going to do 1.008 times 2 plus 16 gets me 18.016 grams. Okay, so if I've got 0.479 grams of copper divided by 63.55, because that's my molar mass, I've got 0.0075 4. I'm going to go ahead and keep some extra significant figures. I like to keep 3 significant figures. So our leading zeros here, these are placeholders. They're important, but our significant are the ones that are the actual numbers. Zeros are only significant if they're in between 2 non-zero digits. So I've got 3 significant figures here, 7, 5, 4. Okay, I've got my chlorine, so 0.533 divided by 35.45. That gets me 0.0150. These are moles. And then my water is 0.273 divided by 18.016, which is 0.0152 moles of water. Okay, so let's do our copper chloride first. So if we're looking at, so I'm going to kind of draw a little squiggly line here to separate those two. So if I'm looking at the ratio between these two, I'm going to divide by whichever one is smaller. So if I'm looking at 0.00754 and 0.0150, well, my smaller one is my copper. So I'm going to divide both of these numbers by 0.00754. Okay, and so I've got this comes out to be 1 copper. And if I do 0.0150 divided by 0.00754, I've got essentially 2, right? So it's 1.989. That's 2 chlorines. Okay, because we need whole numbers. We don't have decimals in our, we don't use decimals in chemical formulas. Okay, so this tells us that our ratio is 1 copper, so Cu, to every 2 chlorines, so CuCl2. Now, copper 2 chloride, so CuCl2, has a molar mass of 63.55 plus 2 times 35.45. Okay, so figuring out the molar mass, 63.55 plus, let's do this, 2 times 35.45 plus 63.55 gets me 134.45 grams per mole. That's my molar mass of copper 2 chloride. Okay, so I know that I had 1.012 grams of copper 2 chloride after heating. So I'm going to convert that into moles. So if I have 1.012 grams, and I know that 1 mole of this stuff has a mass of 134.45, I have 1.012 divided by 134.45, 0.00753 moles of CuCl2. Let's move that over just a little bit so that I can actually write the full. There we go, CuCl2. Now, I've already determined that I had 0.0152 moles of water driven off. So I'm going to look at the ratio between those two. Actually, I'm going to cheat just to save myself some time, and I'm going to notice that it's essentially the same ratio that I had when I figured out my CuCl2 formula. So for every 1 mole of copper 2 chloride, I had 2 moles of water. So that means my hydrate, my full chemical formula, is going to be CuCl2 with 2 moles of water. And there we go. That is my chemical formula. Okay, so let's look at another example. This one says, determine the empirical and molecular formulas for a compound that gives the following percentages on analysis in mass percent. So this is a compositional analysis example, whereas the previous one was a gravimetric analysis example. And then it tells us what the molar mass of the compound is. Okay, so if we remember with our compositional analysis, we are going to assume that we have 100 grams of the sample. That's because 71.65% of 100 is just 71.65 grams. 24.27% of 100 is 24.27 grams. And 4.07% is, you guessed it, 4.07 grams. And that's hydrogen. Okay, so we're going to do the same thing that we did in our previous example. We're going to convert each of these to moles. So 1 mole of chlorine has a mass of 35.45 grams. 1 mole of carbon has a mass of 12.01 grams. And 1 mole of hydrogen has a mass of 1.008 grams. Okay, so let's get out those calculators and see what we get. So 71.65 divided by 35.45 gets me 2.021 grams of, not grams, let's try moles of chlorine. I'm keeping 4 significant figures because all of my numbers have 4 significant figures in them. The 0, because it's in between the 2 and another 2, counts as significant. So I've got 4 significant digits here. Okay, then I'm going to do 24.27 divided by 12.01 gets me 2.021. It's really, It's really 2.0208. Keeping 4 significant figures rounds to 2.021 moles of carbon. And then 4.07 divided by 1.008 is 4.038 moles of hydrogen. Okay, just like before, I'm going to divide by the lowest. Conveniently, 2 of these are both the lowest, which means those are both going to come out to be 1. And then divide by the lowest, which is going to come out to be 2. Because if we do 4.038 divided by 2.021 gets me 1.998, which, since I need whole numbers, is 2. Okay, so my empirical formula is this lowest whole number ratio. So we've got 1 carbon, 2 hydrogens, 1 chlorine. Really, the order that you write these in doesn't really matter. You could chlorine, carbon, H, then the 2 hydrogens. By habit, I know that carbon tends to go first, then hydrogen, then the other things. That's, you pick up on things like that through experience, but you wouldn't be counted wrong if you wrote them in a different order, as long as there's 1 carbon, 2 hydrogens, and 1 chlorine. Okay, so that's my empirical formula. Now we need to check the molecular formula. So I'm told that the molar mass is 98.96. I'm going to see what the molar mass of my empirical formula is. So if I add up 12.011 plus 2 times 1.008 plus 35.45, that will get me my empirical formula mass. It's essentially my molar mass, but based on the empirical formula. So let's see what this comes out to be. Comes out to be 49.477 grams per mole. Now, we may notice that's not the same as what my molar mass is, 98.96. So we have to see how many more times the molar mass is than the empirical formula mass. Now, you may be able to guess that it's going to be pretty darn close to 2. But let's go ahead and check. 98.96 divided by 49.477 98.96 divided by 49.477 comes out to be 2.00012. So it comes out to be 2. That means my molecular formula is 2 times what my empirical formula is. So if I had 1 carbon, now I have 2, so C2. If I had 2 hydrogens, now I have 4, C4. And if I had 1 chlorine, now I have 2, so Cl2. And that is my molecular formula. If you want to check, your molecular formula should always be able to reduce to your empirical formula. If I divide all of the subscripts in my molecular formula by 2, I get my empirical formula. So I know that I probably did it correctly. Okay, let's look at a different compound. A white powder is analyzed and found to contain 43.64% phosphorus and 56.36% oxygen by mass. The compound has a molar mass of 283.88 grams per mole. What are the compound's empirical and molecular formulas? Okay, so similar to my last one, I've got 2 mass percents. I've got the molar mass of the overall compound, so this is going to be set up exactly the same way. I would recommend that you pause the video here, see if you can work it out, and then restart the video to pick up and look at my answer. Okay, so we can treat this problem exactly the same way that we did with the previous one. We can assume the percents are grams if we assume 100 grams of the sample. I'm going to show you a different route that will get you the same answer. In my opinion, it's about the same amount of work, so you can choose either method which works for you. Instead of assuming 100 grams of the sample, we're going to assume 1 mole of the sample, which means that we have 283.88 grams. This is going to give us our molecular formula first, which we can then reduce to the empirical formula if it can be reduced. So it's kind of the opposite that our previous problem did, whereas we assumed 100 grams, worked up to the empirical formula, then got to the molecular. Now we're going to assume that we have 1 mole. We'll figure out the molecular formula and then reduce to the empirical. So I'm going to convert my percents into decimals. So 43.64% is 0.4364, and 56.36% is 0.5636. Multiply each of those by the molar mass because we're assuming that we have 1 mole. So if we have 1 mole of this white powder, we have 283.88 grams. 43.64% of that will get me my grams of phosphorus, and 56.36% of that will get me my oxygen. So let's see what that comes out to be. So if I do 0.4364 times 283.88, I get 123.89 grams of phosphorus. And if I do 0.5636 times 283.88, I get 159.99 grams of oxygen. Now, I'm still going to convert each of these into moles because in order to determine a formula, it doesn't matter if it's empirical or molecular, I still need grams into moles. Okay, so 1 mole of phosphorus is, find my periodic table, 30.97 grams, and 1 mole of oxygen is 16 grams. Okay, so I'm going to do 123.89 divided by 30.97. So I have 4.000, so 4 moles of phosphorus. And I'm going to do 159.99 divided by 16, which gets me 9.999. So 10 moles of oxygen. So again, doing this method gave me my molecular formula first, which would be P4O10. And then if I wanted to reduce that for my empirical formula, I would reduce that to the lowest whole number ratios. So I could divide each of them by 2. So that would get me P2O5 as my empirical formula. So same starting set of data, 2 different routes that you can take. It's entirely up to you because you should get the same answer both times. Okay, for our last type of analysis, we have an example to go with a combustion analysis. So this example says the combustion of 11.5 grams of a liquid produced 22 grams of carbon dioxide and 13.5 grams of water. Determine its empirical formula. So because this reaction produced CO2 and water, we can assume that this has the generic formula of C, where's my C? There we go, X, H, Y, O, Z. Because law of conservation of mass says that what we end with is what we have to start with. So if we end with carbon, oxygen, and hydrogen, we have to start with carbon, hydrogen, and oxygen. So we're going to use carbon dioxide and water, and then whatever's left to figure out what the formula is for this compound. So we've got 22.0 grams of carbon dioxide. Now, this number has 3 significant digits because there's a decimal, so anything after the decimal, whether it's a 0 or a number, is considered significant, as long as it's not a leading placeholder 0. We'll get better at significant figures, I promise. We are going to convert our grams of carbon dioxide into moles of carbon dioxide. So 1 mole of CO2 is going to have a mass that is carbon plus oxygen, which has a mass of 44.01 grams. And then we really don't care about the CO2. What we care about is the carbon. And for every 1 mole or 1 molecule of CO2, we have 1 mole or 1 molecule of carbon. That's because carbon has a subscript of 1. So for every 1 CO2, we have 1 carbon. And then we're going to convert our carbon from moles into grams. Now, the reason we're doing this is because this is how we're going to figure out how much oxygen we also produce based on the original formula. It's going to seem a little silly because we're going to convert to grams and then we're going to go back to moles, but we need the grams in order to figure out how much oxygen we produced compared to how much we started with. Okay, so 1 mole of carbon has a mass of 12.01 grams. So when we do the math, we'll do 22 times 12.011 divided by 44.01, which gets us to 6.00 grams of carbon. Now, we're going to do the exact same thing with our water. So 13.5 grams of water. 1 mole of water has a mass of 18.02 grams. And then in every 1 water, we have 2 hydrogens because it's H2, so there's 2 hydrogens in every 1 water. And then 1 mole of hydrogen has a mass of 1.008. So when I do the math, I'll do 13.5 times 2 times 1.008 divided by 18.02. And that comes out to be 1.51 grams of hydrogen. Now, if I want to figure out how much oxygen, I'm going to take my total amount of liquid. Okay, so I started with 11.5 grams of my unknown liquid. And I've already figured out that 6 grams of that is my carbon, and 1.51 grams of that is my hydrogen. So if I take both of those away, that leaves me with 3.99 grams of oxygen. Okay, so now I know the mass of each of my individual elements. So I'm going to convert them to moles so that I can then get to my formula. So carbon, again, seems kind of silly because we're going a step backwards. 1 mole of carbon has a mass of 12.01. That comes out to be 0.5 moles of carbon. And 1 mole of hydrogen has a mass of 1.008 grams. Should keep my units in. Which comes out to be 1.5 moles of hydrogen. This is moles of carbon. And then I have 1 mole of oxygen has a mass of 16.00 grams, which comes out to be 0.25 moles of oxygen. Now, I'm going to divide by the lowest. So I'm going to divide by 0.25, because if I look at those three numbers, I've got 0.5, 1.5, and 0.25. So my smallest is 0.25. Okay, so that comes out to be 2 carbons, 6 hydrogens, and 1 oxygen. So my empirical formula has the generic formula CXHY07 is really C2H6O. You don't have to include the 1. It is implied simply by writing the formula. Okay, so now that we've looked at several different ways to determine the empirical formulas, let's look at composition of mixtures. So if pure substances are one type of particle, mixtures are 2 or more particles in a substance. They're not chemically combined, okay? So that's the difference between a compound and a mixture. Compounds have chemical bonds between the 2 different components, whereas mixtures have 2 different particles that are not chemically combined. So those particles in the mixture can be elements or compounds. So you can have a mixture of elements, you can have a mixture of compounds, you can have a mixture of elements and compounds, so on and so forth. We have 2 different types of mixtures, homogeneous and heterogeneous. Homogeneous mixtures have a uniform composition, so they're the same throughout. If you were to take a sample of that mixture at any point, it's going to be identical. Solutions are a really great example of this, where we have a solid dissolved in a liquid. Heterogeneous solutions are where we have non-uniform composition. Sand, gravel, things like that would be great examples of non-uniform composition. Mixtures, unlike compounds, can be separated based on physical properties. Compounds have, since they're joined together by chemical bonds, you have to separate compounds using chemical methods. Mixtures, since they're not connected by chemical bonds, can be separated based on physical properties. So we can use filtration, so soluble versus insoluble, large particles versus small particles. We can use precipitation, so where we add something to a mixture, such as a solution where we force precipitation. We'll look at that more later on when we talk about precipitation reactions. Or we could look at distillation. So distillation happens when things have 2 different boiling points. The thing with the lower boiling point will boil first. The higher boiling point will boil later. Again, something else that we're going to come back to when we look at intermolecular forces. One way that we describe the composition of mixtures is through percent composition. So this is looking at the link between the mole relationships, the chemical formulas, and the percentages. And what we can do here is create essentially a conversion factor between the mass of the element and the mass of the compound. We can also look at the composition of mixtures to assess the components of a mixture or the purity of a sample. So a higher mass percent of an element indicates that the impurity has a higher mass percent of that atom. So we can look at what the mass percent should be of a pure compound and then the mass percent of the actual compound. And if the percents aren't the same, then we know that there's some sort of impurity, and that impurity can, the difference in that percent can give us information. So in a compound, the element will be combined with a smaller element. Okay, so let's first look at mass percent. So our example here is carvone, or C10H14O. So what we want to look at here is what is the mass percent of each element in this particular compound. First thing we need to do is figure out what the total mass is, and we're going to just add up the molar mass. Okay, so we've got 10 carbons, 14 hydrogens, and an oxygen. So 10 times 12.01, 14 times 1.008, and 16, which comes out to be 150.212 grams per mole. Now, we're going to look at the fraction of each of these in relation to the total compound. So we've got 10 carbons per every 1 carvone. Okay, so 10 carbons for every 1 C10H14O. So that means we've got 10 times the mass of carbon for every 1 carvone, which is 150.212. We're looking at percent, so we're going to do that multiplied by 100. So when I do 10 times 12.01 divided by 150.212 times 100, I get 79.95% carbon. And then I can do the exact same thing for hydrogen and oxygen. So I've got 14 hydrogens for every 1 carvone. So I've got 14 times 1.008 divided by my total mass times 100, which comes out to be 9.39% hydrogen. And then last but not least should be oxygen. Now, you could add these two up and subtract it from 100 because law of conservation of mass says that if these two make up our carbon and our hydrogen all together, whatever is left should be percent oxygen. But let's go ahead and do the numbers. I've got 1 oxygen for every 1 carvone. Oxygen has a mass of 16. Carvone 150.212 comes out to be 10.65% oxygen. Okay, so pure carvone should be 79.95% carbon, 9.39% hydrogen, and 10.65% oxygen. Now, we're going to go right into our next example. If a sample of carvone was found to contain 12.03% hydrogen by mass, what can you conclude? Well, it's got too much hydrogen. This sample has just over 12%. Our original sample, pure carvone, is 9.39%. Okay, so we can conclude that it's not pure. And since it has something that raises the percent hydrogen, it must contain more hydrogen than it should. So it must contain an impurity with hydrogen. Okay, so we can look at the percent element composition to determine whether it is pure, impure, and where we can go from there. Okay, additional practice, if you're looking for some online additional practice for empirical and molecular formulas and percent composition, You can follow this link to chemquiz.net. The next couple of pages in your packet are going to have some multiple choice and free response questions that you should work through.